Hello students, in this video we'll discuss the Brachistochrone problem. The Brachistochrone problem comes from physics. It says, can we find a curve where a particle slides down as quickly as possible. So let's formalize this a little bit. So what I want to do is this. My idea is that I'd like to find a curve. So I'm going to orient the x-axis this way, the positive y-axis this way. So I'm going to flip the axes to make the problem look a little bit nicer. I'm going to start at the origin, and I'd like to go to this point over here, L, comma, L. And I want to find the curve where if there's no friction along this wire, that a particle with mass m will slide down this curve as quickly as possible. So that's my objective, okay? And so of course I have a function y of x over here, y of x, and I know that by the conservation of energy what has to happen. So let's write down the conservation of energy. By conservation of energy, states that 1/2 mv squared is equal to mg, and then for a particular point y on this curve of height y, mgy. And so solving this equation for v, we see that v is equal to the square root of 2gy. And of course, we also know that on this curve, the velocity is given by the ds dt, which is the change in the arc length with respect to time. So on the curve, we have that this is also equal to ds dt. Okay? So we can solve this equation for dt. So if I solve this equation for dt, I have that dt is what? Is ds over what? ds over the square root of 2gy. Okay? And now I want to put this on what is the arc length parameter on this curve? Well, for this particular function, I know that ds is really what? Is really the square root of 1 plus y prime squared dx. Okay, so that's what the arc length parameter is for a particular curve. So this is exactly equal to what? This is exactly equal to the square root of 1 plus y prime squared over the square root of 2gy dx. Okay, so now if I integrate from 0 to L, I'll find the total time it takes. So the total time that I'm trying to minimize is the integral from 0 to L. I'm going to assume that gravity is equal to 1/2 for the simplicity of this problem. So let's assume that g is equal to 1/2, right? If I assume that gravity is 1/2 in this problem, it will just simplify to y, and that will be the same problem. It's just a constant. It won't change anything at all. So with this assumption, what will happen is I'm going to try to minimize this expression. The square root of 1 plus y prime squared over y dx. Okay? And so what I have over here is I would like to try to find the minimum over all possible functions y that start at the origin and go to the point LL, and I would like to minimize this expression over all such functions over there. So what I'm going to do is I'm going to call this function, so here's another bit of notation. I'm going to use the notation that y prime is equal to p. It's a standard ODE notation that y prime is p. So over here, I have a function over here, f of x, y, and p. And what is that function? That function is just the square root of 1 plus p squared over y. Now, I'm trying to find the minimum over all such of these integrals over here, and to minimize that, we need to use the Euler-Lagrange equations. So the Euler-Lagrange equations state the following. So Euler-Lagrange from the calculus of variations tells me that to minimize over all such functions, this integral expression, this action, I need to satisfy the following for f. F has to satisfy that partial f partial y is the x derivative of partial f partial p. All right, so we can find what is this thing over here? So what is partial f partial y? Partial f partial y is going to be what? So let's take a look. So partial f partial y, like this. So for this function, f sub y is going to be what? Is going to be a negative square root of 1 plus p squared over 2y root y. What will fp be? F sub p is going to be a p over root y 1 plus p squared. Okay? And so now the hard part of this problem is to do the x derivative of this thing, so we were going to carefully do the x derivative of f sub p, right? So what is the derivative of f sub p? So partial, or just the x derivative, or partial, think of it that way, of what? Of f sub p is going to be what? Well, f sub p is three things. It's 1 over the square root of y, it's a p, and it's a 1 over the square root of 1 plus p squared. So let's do them all very, very carefully. So what's the derivative with respect to x of 1 over y? That's going to be a what? That's going to be a negative, what? Negative p over 2y root y. Let's check that, because of course the derivative of y to negative 1/2 is going to be negative 1/2 y to negative 3/2, and then times by the chain rule, the derivative of y with respect to x, which is p. Okay? And then that's times what? That's times another p. So that's times p, not p to the p obviously, but times another p, so that's p squared, right? P squared, and then a what? Then a 1 over square root of 1 plus p squared. That's the first term of the derivative. The next term of the derivative is easy, it's just p itself, so I'm just going to have a plus 1 over root y, 1 over p prime, of course, p prime over root y, and then times what? Times the square root of 1 plus p squared. Good. And then the final term over here is going to be what? It's going to be p plus p over y. And then a negative 1/2. I'm going to have this thing to the 3/2 power in the denominator times the derivative of p squared. The derivative of p squared is what? It's going to be 2p p prime over 1 plus p squared to the power of 3/2 in the denominator. Okay? Great. And so now what we're going to do, and this has to equal what? This has to equal, by Euler-Lagrange, negative square root 1 plus p squared over 2y root y. And so now the trick to simplify this is a complete mess, obviously, but there's one nice trick that we can do that will simplify this dramatically. And what that trick is the following. I'm going to take the entire Euler-Lagrange equations, multiply everything by 2 root y, and then 1 plus p squared to the 3/2 power. Okay? And let's see what happens if we do that. So let's carefully track what we have over here. If we do that, this first term is going to be what? It's going to be negative p squared. And then the only thing that won't cancel out is one factor of 1 plus p squared. So I'll have 1 plus p squared for the first term over there. Now what will remain over here? I'll have a p prime. The root y and the root p will cancel, and I'll be left with a what? With a 2, an extra y, and an extra 1 plus p squared for that next term over there. That's the things that remain over here. Now over here, the 2 is going to cancel over there, so we don't care about that 2 anymore. But we're going to have a negative over here. Now what's going to cancel over here? What will happen is all of the p terms will cancel. One of the y terms will cancel. And then we'll have a what? And then I was missing my what though. So that should have been a what. This over here is not a y, it's a root y, right? P over root y. That's a root y. Okay? So of course the root y will cancel. So I'm going to have a what? I'm going to have a 2. Root y cancels. I'll have a p, and I'll have a y, and I'll have another p over here, and a p prime. And then this whole thing will cancel with that, so all that's left over is just this expression over here. That's p squared. And then what will happen on the right-hand side of the equation? Well, all the y's will cancel. I'm just going to have a negative what? Negative 1 plus p squared, quantity squared. Okay? Now let's do a little bit of bookkeeping over here. So there's a lot of ugly terms, but it's key to note that let's look at this term over here, and then this term over here, right? So what do I have? I have a p squared. I have a 2y, and a p prime. So that term will cancel with this term over here. And then let's sort of expand this out over here. So I'm going to have a negative p squared. I'll have a negative p to the 4th over here. And then I'll have a what? I'll have a 2y p prime. Good. And then I'll expand out everything over here. I'm going to have a negative 1, a negative 2 p squared, a negative 2p squared, and then a what? And then a negative p to the 4th power. Again, the p to the 4th power will cancel from both sides, like so. And I can rearrange this on one side of the equation over here. And what will we get? So we're going to have I'm going to throw the 1p squared over there, and by rearranging it, it's 2y p prime, that stays over here. I'm going to put the 1 over here, plus 1, and then a plus 1 p squared plus a p squared is equal to 0. Now let's look at this equation over here in more classical ODE form, right? So in more classic ODE form, what does this become? This is really saying that 2y, y double prime, because that's what p prime is, plus y prime squared plus y prime squared plus 1 is equal to 0. Okay, we're almost there. I'm going to multiply this equation by a y prime. So if I do that, what will happen? I'll have a 2y y prime y double prime plus y prime cubed plus y prime is equal to 0. And this expression is actually a perfect derivative. What it is this we can check. This is really y plus y times y prime squared. The derivative of this is equal to 0. So let's check and see if that works over here. It says, does that work? Well, what do we have? We have the derivative of y. That will give me this term over here. If I differentiate this first term y over here, I'll have y prime cubed. And if I do the derivative of the y prime squared, I'm going to have a y, a 2y prime, and then a y double prime. So it exactly works. So what this tells us is it tells us that y plus y prime squared is a constant. So y plus y prime squared is equal to a constant c. And then it turns out that if we solve this equation over here, we're going to have so we're going to have that y prime squared is going to be what? It's going to be c minus y over y. And therefore, y will be the square root of this thing. So in other words, this ODE is a separable ODE. And we know what the solution to the separable ODE is. From a previous video, we know that the solution to this ODE is exactly an inverted cycloid. So check out that previous video to make sure that you can see that you can solve this equation over here, this separable ODE, and by the separation of variables technique and making a trigonometric substitution to put it into the form of a cycloid. So we see that the solution to the Brachistochrone problem is an inverted cycloid. Thank you very much.